So, time for further discussion on electric flux now. In our previous video, we were discussing about the basic concept of electric flux. We also discussed the fact that electric flux is essentially the number of lines of force passing through an area. Now, in this video we'll be going a little deeper into that concept, a few examples, and later on we'll be talking about Gauss's theorem. Now, as far as the concept of flux is concerned, there are a few things that you need to remember. And the first thing is that if there's a surface over which electric field is tangential at all locations, if electric field is tangential at all locations of a surface, then the flux through that surface will be zero. No lines of force will be passing through that surface. For example, if we think of this board here and the electric field is tangential to its surface at all locations, then no electric field lines will be piercing through it, and therefore the flux through this surface of the board would end up being zero. Also, the other simplification in calculation of flux would be that if you have a surface over which electric field has a constant magnitude at all locations of that surface, and not only is it constant in magnitude but is also normal to or perpendicular to the surface at all locations of the surface, then over that surface electric flux would end up having a fairly simple calculation. You would simply have to multiply the area of the surface with the magnitude of the electric field over the surface. I'll repeat this second point. If over a surface electric field remains constant in magnitude at all locations of the surface, and also the electric field happens to be normal to the surface at all locations of that surface, then the flux is simply the product of magnitude of the electric field with the surface area. So keeping these two simplifications in mind, we will be calculating electric flux for a few in a few examples here first, and then we will move on and discuss what we know as Gauss's theorem. Now, let's first take a simple example. Let's say we have an electric field given by 4I cap plus 2J cap plus 3K cap, let's say. And these are our coordinate axes, x, y, and z, or z, whatever you call it. And over here we have been asked to calculate the electric flux to a particular surface, and surface is a plane surface here. Let's say we have this square shaped surface. This square shaped surface here has a side of 2 meters, and this is the electric field. This surface is entirely in the YZ plane. This surface here is in the YZ plane. This is the surface, and we are asked to calculate the electric flux through this surface here. Now, over here in this particular example, the electric field is constant, although it is not normal to or perpendicular to the surface, but it is indeed constant. Now this electric field has three components. One is the x component. Now the x component, which has a magnitude of 4, is indeed perpendicular to the surface. This is the x component of the electric field. The y component, which is 2 in magnitude, is in the upward direction like this, and this component is indeed tangential to the surface. Now looking at the third one, 3, that's in the z or z direction, and this component, having a magnitude 3, is also tangential to the surface. Now these components which are tangential to the surface will not produce any electric flux through the surface. So the only component of the electric field here which is producing a flux through this surface is this x component. And since this x component is constant everywhere throughout this surface, at all locations this component has a constant magnitude of 4, and therefore the flux through this surface would be equal to this 4 times the surface area, and the surface area is 2 times 2, and that's 4 as well. And so the flux here comes out to be 32 units. Now what would be the unit of flux? Unit of field, electric field, is Newton per Coulomb, and then you multiply with area, so Newton per Coulomb times meter square. So that's the flux here. Now there is another way of looking at this particular calculation here. The other way of looking at this calculation is that we can think of an area vector for this entire area. Now when electric field has a constant magnitude and the area is a plane area, this area is a plane area, it lies entirely in the YZ plane. So when the area is a plane area, we can assign an area vector to that entire large area. Normally we assign area vectors to tiny area elements dA, but when you have a large plane area, we can assign an area vector to the entire area, but this can only be done under certain circumstances. As I mentioned, the area should be a plane area and the electric field should be constant. In that kind of a case, we can have a single area vector here. This area vector would be equal to the magnitude of the area, that is 2 times 2, 4, and the area vector here would have a direction in the positive x axis. It would have a direction parallel to the positive x axis. So this would be 4 times I cap. That's the area vector. And so flux can be now calculated as E dot A. Normally we define flux as E dot dA, but here we can have E dot A because E is constant and area is a plane area. So now this flux will be E times A, so E is 4 I cap plus 2 j cap plus 3k cap, and we're multiplying this, doing a dot product with area vector which is 4 I cap. So area vector is 4 I cap, and therefore flux would be 16 Newton per Coulomb meter square. It seems I made a wrong calculation in the first case. I think the area vector was 2 times 2, that's 4, and the field was 4. I don't know where this 2 came from. So 4 times 4 should have been 16 here as well. Sorry for the wrong calculation. So here it was simply a product of this component of field with the area, which was 2 times 2. So 16. I don't know. I made a mess introducing an extra 2 there. So anyway, this is the concept of what we call electric flux. Simple example here, just to begin with. Let's have a more complex case of calculation of flux. In this particular example, the field here was constant. Now what we'll do is we will take up an example where the field is variable. So to make life more interesting for us, we'll take up an example now where you have a variable field, but we'll also not be making things too complex, and therefore we are not going to have a curved surface. We'll still have a plane surface. Let's say we have the same area as we did in the previous example. So this is x, y and z or z, and the same old plane area, square plane area of 2 meter by 2 meter in the yz plane. So this is a plane area, again 2 meter by 2 meter, and we are being asked to calculate the flux here due to this electric field. Let's say it is 2y I cap. So this field is variable. It varies with the y coordinate, plus 3x j cap plus 4z k cap. Now, if we look at the components of the electric field, now it has 3 components. It has a x component, it has a y component, and it has a z component. It has an x, a y and a z component. Now the y and the z components are actually tangential to the surface. So the y and z components do not produce any flux. The only component producing any flux here is the x component. So we'll be calculating the flux for the x component alone. Now because the x component here is variable, we cannot use the process that we used in the last example of simply multiplying this magnitude of field component in x direction with the area, or taking the dot product of the area vector with the field component. That same process is not applicable here, cannot be applied. We need to use integration. We need to take small area elements and then calculate flux through those small area elements, and then do a summation of flux through all the area elements. This is what needs to be done. Now the area element has to be thought out well. You have to think about what area element you're taking. So to describe the area element, let me first redraw this plane surface here. I'm drawing this surface. This is the surface. We have the y-axis here and the z-axis here. So I've assumed now that the plane of the board is the YZ plane, and the x-axis would now actually be perpendicular to the plane of the board in the outward direction, and the side of the square is given to be 2 meter. Now the electric field is in positive x direction, and positive x direction means coming outward from the plane of this board. So the electric field is now outward from the plane of this diagram, but unfortunately for us, the electric field has a variable magnitude, and therefore we have a bit of a task on our hands. Now we have to think of an appropriate area element which would help us calculate flux more easily. Now the idea should be to take up the largest possible area element, because larger the area element, the lesser the work that would have to be done in integration. So we need to have the largest possible area element for calculating flux through an element and then doing a summation later on. So what we should be doing is we should be thinking of looking out for the largest possible area element in which electric field could still be assumed to be pretty much constant. Now such an area element over which electric field, the relevant component of electric field, has a constant magnitude, would have to be an area element in which y coordinate is constant. We have to think of an area element in which the y coordinate is constant. So think of this area element. In this area element, which is parallel to the z-axis, the y coordinate, y over here, is constant. So since y is constant here, the electric field component in the x direction, that is perpendicular to the plane, that x component of the field is constant. Therefore we would have an easy time calculating the flux through this area element. And then what we'll do is we will consider all the area elements all the way from the bottom here all the way up to the top. We'll consider lots and lots of such strip shaped area elements. We'll calculate their flux and then do a summation. Now the flux d phi through this particular area element, the flux d phi through this area element is going to be the magnitude of the electric field throughout this element. Now since y has the same value, we can use one single value of the electric field here, that's 2y. That's the electric field throughout this element. We multiply this field with the area of this element. Now the area of the element will be the width of the element, that is dy times this length. Now this length of the element is obviously 2 meter, so the area is 2 times dy. The length of this rectangular strip is 2 meter, the width is dy, so 2 times dy, that's the area of this particular element. So that's the flux through the element. Now we'll be doing a summation of electric flux for all such area elements to get the flux through the entire area. So phi would now be equal to 2 times 2, that's 4, into integral of y dy. Constants come out of the integration process. Integration of y dy will now be, we are integrating y dy, and we have to integrate for all the elements on this body. The lowermost element here if you consider this element, for this element y is 0, and for the topmost element y will be equal to 2. So from 0 all the way up to 2, and therefore the flux phi will now be 4 times the integral of y dy, which is y square by 2, and the limits of this integration process will be from 0 to 2. So phi is 2 times y square. Now in place of y, when we substitute 2, we have 2 square minus, we substitute 0 in place of y square, we get 0 square. So this is 4 times 2, and so the flux is 8 units of flux. So this is another example on calculation of flux. Now let's think of more slightly more complicated shapes. But before I do that, let's describe what is called a closed surface, because we're now going to move on to curved surfaces, and with curved surfaces it will be more fun to be talking about surfaces that are closed, because that's what leads us to Gauss's theorem. So let's think of closed surfaces. Now what's a closed surface? A closed surface is one that is closed on all sides. You know, for instance, if I consider this cushion here, this cushion has, you know, it's a solid object. It has a surface which is closed everywhere. So we have a closed surface. The surface of this is closed at all locations. But if I open the zipper and I open this surface, then it becomes an open surface. So with the zipper closed, it is now a closed surface. It's closed everywhere. But if I open the zipper and open this up, it becomes an open surface. So we are looking at a surface which is closed everywhere. It's a three-dimensional surface, but it's a closed surface. Now with closed surfaces, there is one interesting thing that we do, and that is, in case of closed surfaces, the area vectors are always taken in the outward direction. If you have a tiny little area, you know, let's get this cushion back again. If for instance, you know, you look at these little areas here, if I am to take an area vector representing this area, that area vector would be outward from the surface and not inward inside the surface. So if I am to take an area vector representing this area, the area vector would be outward from this surface. Now as I said, the area vectors will have to be always outward from the surface of a closed surface. That is just by convention. It could very well have been decided to take area vectors inward, but the convention globally is to take area vectors in the outward direction, and that's what we'll be doing here. Area vectors will be taken in the outward direction, and you know, accordingly flux will be calculated. Now we start with a fairly simple case of a spherical surface. So let's have a sphere to start with. Now in this sphere, let me draw this sphere. This is the sphere that we are thinking of. So we've got this sphere, let's say it has a radius r, and to create an electric field, what we do is, at the center of the sphere, I place a positive point charge plus Q. Now this plus Q charge has been placed at the center of this sphere here. So this charge creates an electric field in this space, and we are interested in calculating the flux due to this charge on this entire surface, right? Now, there is a simplifying feature in this particular problem, and that is that if at any of the locations on the surface we consider the electric field, that electric field would be normal to the surface. So since the electric field of a point charge is directed radially outward from it, it would be normal to the surface at all the locations of the surface. So the electric field is normal to the surface at all locations of the surface. Another simplifying feature in this calculation is that since all the points on the surface are at exactly the same distance from the charged particle, the magnitude of this electric field would also be same at all locations. So, this electric field E, which I have mentioned at two of these points, it has a magnitude that's given by 1 by 4 pi epsilon naught Q by R square. So the magnitude of this electric field is same at all these locations, and it is also directed normal to the surface at all the locations. Now since we have an electric field which has the same magnitude at all locations of the surface and also is normal to the surface at all locations, in such cases flux calculation is actually very, very simple. You simply multiply the magnitude of electric field with the surface area. So flux equals magnitude of field times the surface area. But remember one thing, this works only when E, the field, is constant all over the surface and normal to the surface at all points. Otherwise, you have to use an integration process by taking flux of tiny area elements. Now, this is a simple calculation for flux here. E would be equal to, phi would be equal to E, that's Q by 4 pi epsilon naught R square times the area, which is 4 pi R square for a sphere. Some cancellations happen and we get flux which equals Q by epsilon naught. Now this is kind of surprising, because this flux does not seem to depend on the radius here. This flux is looking like it's independent of the magnitude of this radius. Now, is that going to be the case for all kinds of surfaces? We had in this particular calculation, we had a constant electric field which was normal to the surface at all locations of the surface. So is this going to be the case for all kinds of surfaces, for all kinds of shapes, where this simplifying assumption is not there? Would it still be true that the flux is Q by epsilon naught? Now, we'll be examining this possibility in our next example. Now what I am going to do in the next example, we're going to make a very small change in what we are looking at. So we still have the same sphere, but what's going to change now is the placement of that charged particle which we had placed at the center. Now this time the charged particle which we had placed at the center earlier, we are going to place it off center. So this time now the charge is placed over here. Let's say, for instance, it is placed at this point. Now, what is the flux through the spherical surface? I'll play a little clever trick here. I'll draw a smaller sphere of radius r prime around this charge, keeping the charge at the center. So what I've done is I've drawn a smaller sphere of radius r prime, keeping this charged particle at the center. Now the flux through this sphere would obviously be q by epsilon naught, as we have just calculated in the previous example. Now we are interested, as I said, in calculating the flux through this sphere first. Now the flux through this sphere would be calculated in exactly the same way as we calculated in the previous example, and therefore the flux through this surface, this chota sphere, this tiny sphere here, the flux through this one would be q by epsilon naught. Now let me draw all the electric lines of force that are coming out of this charged particle. Let's say this is the first one, then the second one, and then the third one, and so on and so forth. I'm going to count all these lines, and we keep doing this. I've drawn all the lines of force that are coming out of this surface here. Now what I observe is, we were counting all these lines, and the last one is number q by epsilon naught, right? Now we'll notice something interesting. What is that? Whatever be the number of lines of force that are coming out of the smaller sphere, the same number of lines are coming out of the larger sphere as well. None of these lines stop anywhere. None of these lines stop anywhere between this surface and this surface, nor do we have any new lines coming out anywhere from any of these points. So the flux through the larger sphere would have to be the same. So the flux through this sphere remains q by epsilon naught, which is very interesting. So even when the charge was not placed at the center of the sphere, the flux still remained q by epsilon naught. Now we've worked this out for a spherical shape. Let's now have an arbitrary shape and calculate the flux through a closed surface of arbitrary shape. So this time we now have a closed surface. It has an arbitrary shape, and we place a charge q somewhere inside it. So we have a charge q kept inside a closed surface, and we are calculating the flux through this. Now to calculate this flux, I keep this charge at the center of a smaller sphere. I draw this sphere. Now I know the flux through this surface would be q by epsilon naught. And then looking at the lines of force that are produced like this, what we'll observe quite easily is that the number of lines of force passing out through the smaller sphere is the same as the number of lines of force that are coming out of this larger sphere surface. So the flux through the sphere happens to be Q by epsilon naught, and therefore the flux through this surface is also Q by epsilon naught, depending neither on the radius or the size of the surface nor on the placement of the charge. So this is beginning to get pretty interesting. We have a closed surface of an arbitrary shape, and we figured out that the flux through it equals Q by epsilon naught, where Q is the charge that's kept inside it. Now, is this universally applicable for all kinds of closed surfaces, for all kinds of charged particles, for all kinds of placements of the charged particles? Well, let's examine this in a little more detail. Now, what we have so far learned is that if the charged particle is placed inside a surface, the flux through that closed surface happens to be Q by epsilon naught. Now, before going any further, I want you to understand one little point, that if we have a closed surface here, then we are bound by convention to consider the area elements to be represented by outward area vectors. So the area vectors have to be outward and never quite inward. So if at any location we have an electric line of force coming outward, there is an electric line of force coming outward, that means the electric field is in this direction, then the angle between the electric field vector and the area vector would be an acute angle, and therefore the flux would be positive, because cos theta would be positive. So when electric field lines come out of a surface, they produce a positive flux. Now let's think of another example where we have this area element, which obviously is represented by an outward area vector, but at this location electric field lines are inward. That is, the electric field, let's say, is this is, let's say, an electric field line, and the electric field vector is now inward, right? Now the angle between the area vector and the electric field vector, the angle would be obtuse. It would be larger than 90 degrees or pi by 2 radian, and therefore the flux over here would be E dot dA, that's E dA cos theta, E dA cos theta. So since theta is greater than 90, when angles are obtuse, greater than 90 degrees, cos theta is negative, and therefore this d phi, the flux, would have to be negative. So when electric field lines are coming out of a surface, flux is positive. When electric field lines are entering a surface, flux is known to be negative. So if you have an electric field line coming out of the surface, its contribution to flux is +1, and when an electric field line is entering a surface, its contribution to flux is -1. So electric field lines leaving a surface in the outward direction produce a positive flux. Field lines entering a surface produce a negative flux. One line coming out, the contribution to flux is +1. A line coming into the surface, contribution to flux is -1. So keep this in mind, and now we'll look at our next case where we'll be examining the flux through a closed surface of arbitrary shape, but this time we'll be keeping the charge outside the surface. So we have now another closed surface, right? It's a closed surface, and the charged particle that we are considering is kept outside it. Let's say the charged particle is now kept here. With the charged particle here, if we are to calculate flux, life gets fairly interesting. Let's draw these lines of force that are coming out of this charged particle. Now with all these lines, as they enter here, their contribution to flux is -1, but then as they leave the surface, the contribution to flux is +1. So it's -1 here, +1 here, -1 here, +1 here. And we all know when we add -1 and +1, we get 0. So the flux produced due to this charge over this entire closed surface would end up being 0, because either the lines do not enter the surface at all and therefore contribute 0 flux, or the lines have to enter as well as leave the surface, producing a 0 net flux in any case. So what we have seen is that if we have a charged particle outside a closed surface, its contribution to flux would be 0. Irrespective of where the charged particle is kept, irrespective of the shape and size of the closed surface, its contribution to flux through this surface would have to be 0. So there are two things we have learnt here. First is that if we have a closed surface and we have a charged object kept inside it, having a charge q, then the flux through the surface due to this charge inside it would be q by epsilon naught. And if the charged particle is kept outside the surface, then the flux through the surface would end up being 0. Now this statement, statement of fact that I just made is actually called Gauss's theorem. Now what Gauss's theorem really says is that if we have a closed surface, this is a closed surface, and we have inside it charge qi, I for inside, and we have charges outside it as well. Let's say qo, O for outside, so charges are there outside it, charges are there inside it, and we are interested in calculating the flux through it. Now at any location on this surface, let's say this is the electric field. Now this electric field is the net electric field at this location due to charges inside as well as charges outside the surface. So this is the net electric field here. Now consider a tiny area element. Let's say we have this area element and its area vector is dA. Then the flux through this entire closed surface would have to be the we'll be calculating the flux over this entire surface. Now, as we do that, let's consider this tiny little area dA and the electric field E, and calculate a dot product of E with dA. Now, I've already mentioned this E is the net electric field due to Qi as well as Qo. And then after calculating this flux through this tiny area, we calculate this flux through the entire surface. This S indicates that the flux here, this integration is being carried out for flux over the entire surface. We are not leaving out any part of the surface. This is being calculated over the entire surface. Also, we are calculating this over the entire closed surface, and I indicate that by drawing this little circle here. This indicates that we are calculating the flux over a closed surface, and S indicates that the integration is indeed being carried out over a closed surface. Now this will come out to be Qi divided by epsilon naught. So even though this field was due to charges enclosed inside the surface as well as charges outside, so this field is because of Qi as well as Qo, but on the right hand side of the equation, once we have calculated this total flux, it comes out to be charge enclosed inside the surface divided by epsilon naught. And this expression here is called Gauss's theorem. Now, Gauss was actually a mathematician and lived before the time when electric fields were understood, or even Coulomb's law had come up. So Gauss actually had given this kind of a calculation for gravitational fields and not for electric fields. This was adapted in electrostatics by Maxwell, who did pioneering work on the theory of electromagnetism, and therefore this is actually Gauss's theorem, but a version that was modified by Maxwell for adaptation in electromagnetism. Now this theorem is kind of an alternate version of Coulomb's law really. So you either state Coulomb's law or you state Gauss's theorem. You're actually stating pretty much the same thing. So they're completely compatible with each other. They are actually almost the same thing. It's actually just a different way of looking at Coulomb's law. Now, since this video is beginning to get a little too long, I will conclude here at this point, where we have arrived at Gauss's theorem. In our next video, we are going to have a look at some applications of Gauss's theorem that you can get in typical physics exams, be it school or university exam, or even JEE exam or NEET exam. You can get certain typical kind of applications on Gauss's theorem. We'll be looking at those. I would again thank you all very much for watching this video. I hope you enjoyed this discussion on Gauss's theorem as much as I did. I really did enjoy this. It was fun doing this video. I hope you had fun too. And also I would suggest that you come up with your queries, your suggestions on how I should be doing future videos. I have made some slight changes. I have started sitting down on my chair and doing these videos because I think it gives these videos a more conversational feel, more relaxed feel. I'm hoping certainly that this is giving you a feel that you're conversing with me rather than sitting in a conventional classroom. So it has more of what one might call chill factor. So I'm certainly enjoying it, doing it this way, and I'm looking forward to your suggestions on how perhaps I can make these videos even better. Also keep posting your queries, any difficulties that you might have had with any of the explanations that I give. If something was not clear, perhaps I can address your issues in the upcoming videos. All the same, thank you very much for watching this video, and please like and subscribe as it helps the channel grow and encourages me as well in doing better work in the time to come. Thank you very much.